Hey guys, welcome back to another interesting topic. Today's topic is about carry-lookahead adder. So carry-lookahead adder is mainly to overcome the drawbacks of ripple carry adder. So ripple carry adder gives us a propagation delay. So in carry-lookahead adder, we will improve the speed. Okay, the main target is to improve the speed. To improve the speed, we are adding some extra hardware. So adding extra hardware means we need to buy more stuff. That means we need to buy more gates. That will increase the cost. So here is the ripple carry adder, as you can see over here. So FA 3, 2, 1 and 0. So as you can see, FA1 full adder 1 is dependent upon full adder 0 so that it can get C in, and FA2 is dependent on FA1 so that it can get C in, and FA3 is dependent upon FA2. So every full adder is dependent on the previous full adder. As you can see over here, it is dependent on the previous stage of full adder. As a result, we will be getting the delay, propagation delay. So carry need to be propagated from this to the last full adder. As a result, the delay is more in carry generation. If we can predict what value will be coming over here, if we can generate whatever the value will be coming over here based upon the C in, then we can save a lot of amount of time. For example, if each full adder takes 2 seconds to generate the carry, so if C0 is generated at 2 seconds, so C1 will be generated at 4 seconds, 2 plus 2, and C2 will be generated at 6 seconds, 2 plus 2 plus 2, and C3 will be generated at 8 seconds. What if now, if we get all the C-ins at a single time, that means parallelly if we get all C-ins at a single time, that means at 2 seconds we are getting all the C-ins. That means the output will be generated at 4 seconds to generate the normal carry time. That's it. We are reducing the time by 50% approximately based upon this example. Okay, so how are we gonna generate our hardware so that we can reduce the amount of this speed and delay generated in the ripple carry adder? So before going to carry-lookahead adder, I want you to know this simple technique. So let us consider A and B as 2 bits. A and B as 2 bits. So 2 bits means 4 combinations in binary, 0 0, 0 1 and 1 0 and 1 1. So in these combinations, which one will generate the carry? Okay, this when we add this, which one will generate the carry? 1 plus 1, 0, and carry is generated over here. This is the carry and this is the sum. So this carry will be given to the next bit. Okay, so now if the carry is over here, if this carry is here or here, what does this combination does? 1 and 0 will propagate this carry to next one. Okay, so the value will be 0 and 1. So here it is 0 and 1. So from this small example, I want you to understand that whenever both A and B are having 1, then the carry is generated. Okay, carry is generated. Whenever A and B are complement of each other, okay, whenever both are complement of each other, carry is propagated. Okay, carry is propagated over here and carry is generated over here. So A and B are 1, that means A dot B equals to 1. Okay, when both are 1, it's an AND gate. So over here it is like XOR gate, so A XOR B. So as you can see from this small example, we can say that so generation is done using AND gate and propagation is done using an XOR gate. So to better understand more clearly, I am using a truth table of full adder without using the sum. So whenever Cout is generated, so let's have a look. So Cout is generated over here and here and over here and over here. So these are the 4 conditions when Cout is being generated. So as you can see, just take a look at this 2 and this 2 separately. Okay, whenever A and B are complement of each other and C in is 1, whenever A and B are complement of each other and C in is 1, we are getting the value of Cout as 1. And in this case, whenever A and B are 1, without irrespective of Cin, then the carry is 1. So by this we can write the equation of Cout as, okay, so equation of Cout becomes like this: AB plus A XOR B and Cin. So this is the general expression of Cout. So we have discussed one thing previously, that this is generation. So this is, I'm writing as generation, and this is a propagation of carry. Okay, I hope you remember this. So don't forget that propagation is XOR, generation is AND gate. So now let us look how this will be helpful in generating all the carries at once parallelly. So this is a full adder. As you know, this is a full adder with the 3 inputs A, B and C. So this is a generalized expression, means generalized value. Ci plus 1 equals to Gi plus Pi into Ci. So Gi is A into B and Pi is A XOR B. Okay, so Gi is equal to Ai into Bi and Pi equal to Ai into A XOR B. So this is a full adder circuit. We will get Pi over here and Gi over here, and we are having some extra delay of AND gate and OR gate to get Ci plus 1, which will be common in every stage. So which will be common in every stage. So to generate the C0 over here, a certain amount of delay is there, so that will be common in every stage. But if we get the Cin at the same time parallelly, then we can reduce it. So let's see how it's done. Since we have got our expression, so let's start our writing down carry out from C0 to C4, how we will get the carry outs. So this is our generalized expression: Ci plus 1 equals to Gi plus Pi into Ci. So our input carry is C0, that is our input carry, which will be given by the input. So as you can see over here, so C0 is our input carry for this case. Now C1 will be G0 plus P0 plus C0. Substitute 0 over here, then we will get C1. Now substitute 2 over here, that means I equals to 1. That means C2 equals to G1 plus P1 into C1. Now what is C1? C1 is this. So substitute C1 over here. Now C2 will become, so this is the value for C2 when we get our C2 value when substituting C1. So but here you can see that, you can notice one thing: our aim is to not use the previous carry value. Our aim is not to use C1 over here. As a result, we are not using C1 over here. G1 is A1 into B1, P1 is A1 XOR B1, and G0 is A0 B0 plus P1 is what? A1 XOR B1 into A0 XOR B0 and C0. From this expression, you can clearly notice that we are not using C1. The previous carry value is not being used over here. That's the advantage. But here we are using some more XOR gates and more AND gates. That's the only drawback. That means we are using more hardware to get the things faster done. Okay, so now let's look at C3. So C3 value is, I have written it down already. So C3 is, substitute 2 over here. So C3 will become G2 plus P2 plus C2. Okay, we already got C2 over here, so substitute it in C3. So we got G2 plus P2 plus C2 and substitute them, and we are going to get this expression. And similarly for C4. So now I'm going to show you how this is going to work for us. So as you can see that the carry is generated within 2 levels. So every level, as you can see, this is C1. So C1 is dependent on OR gate and AND gate, and C2 will also be looking like similar to C1. So C2 will also look similar to C1. So as you can see, we have only 2 level. Only 2 level delay is there in here. Don't forget that. Only 2 level delay is there. And even in C3 and C4, we have only 2 level delay. As you can see, there is 1 level and 2 level. There is 2 level delay. The number of gates are increased, but we are getting the carry at a 2 level faster. Okay, faster compared to ripple carry adder. Propagation delay is reduced and number of gates are increased. So this is our carry-lookahead adder generator. So as you can see, the internal diagrams which I have shown, C1, C2, C3. So C1 will look like this, C2 will look like this, and C3 and C4 I've shown you already. So C3 and C4 will look like this. All this AND gates and OR gates are present in carry-lookahead generator, which is a block diagram. So this is the block diagram where I have shown you, where all the our C1 generation is there inside over here. So sum is generated like this: Pi into Ci, Pi XOR Ci. You know Pi and you know Ci. So it will not take as much time in the ripple carry adder, where it will depend upon C2 and C3, because C3 is generated based upon C0 and the present values. So the time delay is reduced. In here, the problem with carry-lookahead adder is that number of gates are increasing. As you can see, in ripple carry adder, for a 4-bit we use 20, as in carry-lookahead adder we use around 26 gates. So we are using some extra gates over here to reduce the time. So okay, this will matter in chip design when there is a less area. At that time, carry-lookahead adder will give some problem, so we need to go back to our ripple carry adder. But to get the faster done, so we will go with the carry-lookahead adder. I hope you have understood valuable carry-lookahead adder. And if you have any doubts, you can comment down below. Thanks for watching, and please do subscribe.